Solving a distance rate time problem using a system of linear equations. A motorboat travels 360 kilometers in 6 hours going upstream and 602 kilometers in 7 hours going downstream. What is the rate of the boat in still water and what is the rate of the current? To get a better grasp of what's going on, it's probably best to draw a couple of sketches. So let's say this dot represents the boat going upstream. And we have two cases. So we can draw the stream again, and then this one would be downstream. Now let's look at downstream. Downstream, in some ways, is a little bit easier to understand because you have the rate of the boat in still water going like that. And then the current is pushing it a little bit. This blue arrow can't be bigger than the red arrow, because if the blue arrow was bigger than the red arrow, the boat would never make it upstream. So why don't we give these a few names? Why don't we call this red arrow R, and we'll call this blue arrow C. And we're going to go ahead and define our variables. Let's define R first. Define R to be the rate of the boat in still water. What's C? C must be the rate of the boat. I'm sorry, it's not the rate of the boat. It's the rate of the current. When the boat is going upstream, we know that the arrow here has to be less than the arrow of the red plus the blue. So it's got to be a little bit shorter. So it's going upstream, the boat's actually going slower. So it's represented by a shorter arrow. Why don't we organize our data? Let's draw 3 rows and 4 columns. Four columns. Let's call this rate times time is equal to distance. We want to label upstream, and we want to label downstream. So there's action going upstream, there's action going downstream. Let's do downstream first. The total rate of the boat going downstream is got to be faster. So we write that with R plus C. Well, going upstream, it can't be R plus C. The boat can't go any faster. In fact, it's got to be going slower. How much slower? It's got to be going slower by the rate of the current. So in order to indicate the slower rate, we simply write R minus C. Now let's label our times. Upstream, 6 hours. Downstream, 7 hours. Distance going upstream, 360 kilometers. Distance going downstream, 602 kilometers. And now we're in business. We have 2 equations, 2 unknowns. Quantity R minus C times 6 is equal to 360. Second equation, the quantity R plus C times 7 is equal to 602. Let's rewrite these equations. we have 6r minus 6c is equal to 360. Let's simplify this. Let's divide the entire equation, or both sides of the equation, by 6. So we get r minus c is equal to 60. I'm going to call this equation 3. This equation here, this is 7r plus 7c is equal to 602. I'm going to call this equation 4. I'm going to relabel this actually. I don't want to call that equation 3. I see something better. We can see that this is r is equal to c plus 60. Let's call this equation 3. I'm going to sub 3 into 4. Seven times r, but that's c plus 60, plus 7c is equal to 602. What does that mean? This means we have 14c plus 420 is equal to 602. Balance. 14c is equal to, let's see, 2, 5, 8, 182. Do some long division, not a problem. Once, 4, 2, 3, 42 here. Remainder 0. So c is equal to 13. 13 kilometers per hour. How do we get r? Well, r is equal to c plus 60. So let's go back to equation 3. C 13 plus 60. 73. Let's answer the question. Rate of the boat is 73 kilometers per hour, and the rate of the current is 13 kilometers per hour. Does this problem make sense? You know, what if the current was faster than the rate of the boat in still water? Would that be possible? You want to ask yourself that. In other words, the current was always between 0 and r. The current couldn't have been faster than the rate of the boat in still water.